A prompt optimizer just dropped that costs 15 cents to run, beating a baseline that costs $13 for the exact same task. This performance was achieved with zero labeled training data. There were no answer keys and no predefined validation metrics to score the model's attempts. Instead of relying on ground truth, the system uses a single operational mechanism, one language model judging the output of another. The removal of the labeled data tax changes the cost structure of optimization. The question is whether this represents a structural breakthrough in architecture or a cheaper way to drift toward incorrect results. I'm the host of Bearded AI Guy. Today, we are looking at foundational research tracked by the human architect. The paper Self-Supervised Prompt Optimization appeared on arXiv in February 2025 and was included in the findings of ENLP later that year. Since its release, researchers have developed a series of Descendant frameworks based on these same principles, including PDO, PREPO, and GEPA. We are examining a specific result that changed how researchers calculate and apply optimization signals in production. The traditional pipeline runs variance against a validation set, scoring against ground truth to find a winner. This recipe, standard for TextGrad and DSPy, is effective but tethered to labels. It's unusable for open-ended tasks like roleplay, where subjective answers can't be scored by a static key. SPO's primary contribution was testing whether the optimization engine could function without that answer key. Imagine tasting two different versions of a recipe. You can pick which one is better without needing a master reference dish to tell you what the perfect version should taste like. That pairwise comparison is the technical logic operating inside the self-supervised loop. SPO runs the best prompt and candidate on unlabeled questions, feeding both to an evaluator. The judge generates a binary accept-reject signal. Winners replace the champion via hill-climbing logic. The outputs double as the judge's signal and the raw text the optimizer reads for improvements. By making outputs self-referential, SPO removes the requirement for ground truth data, allowing for optimization in domains where labels don't exist. Consider two students taking an exam. One spends pennies on a quick review, while the other pays for expensive tutoring, and the cheaper student ends up with a higher score. To understand why that is possible in prompt engineering, we have to look at the benchmark economics. This chart breaks down cost per dataset across 5 closed benchmarks, using 8 LLM calls per iteration over 10 iterations. SPO operates at roughly 1% of the cost of TextGrad, achieving a higher average score of 66.9 compared to 63.9. This shift in cost structure makes continuous, automated optimization a viable option for production environments that previously could not justify the expense. A student who memorizes a specific practice quiz may score perfectly on that drill, but they will likely fail a generalized final exam they haven't seen before. That same risk of memorization exists in self-supervised optimization. Performance peaks early, but degrades if the optimizer runs too long. The system overfits to the 3-question mini-batch, sacrificing generalization on broader benchmarks. Success is conditional, relying on a strictly limited search budget and a strong judge model that ignores superficial patterns. Label-free optimization includes a built-in risk of overfitting, which requires engineers to strictly monitor and limit how many iterations the engine performs. While SPO demonstrated that label-free optimization is possible, the research that followed focused on the more difficult challenges of search and feedback. Once the basic viability of the signal was proven, the field began to address the limitations of the judge model. Research split into 2 directions: seeking deeper signals and implementing complex search logic. GEPA uses reflective feedback from execution traces, gaining 12 points on complex tasks. PDO reframes optimization as a dueling bandit problem, using multi-model rescoring to prevent circular judging artifacts. SPO provided the proof of viability for label-free optimization. The technical conversation has now moved toward the mathematical methods required to keep that judge honest. Engineering in this space requires balancing 2 facts. Ground truth labels are often too expensive to acquire, but subjective proxies are fragile and prone to drift. These pillars represent the core challenge. SPO works when judge preference strongly correlates with actual task quality, but for hidden objectives or long-horizon tools, an evaluator only seeing text becomes unreliable. The bridge between proxy and goal breaks. Optimizing for what a judge likes rather than what the task requires will eventually lead to a decline in actual system performance. To prevent this, practitioners must cross-validate their evaluators against held-out sets and strictly control the length of the optimization process. Subscribe to Bearded AI Guy for more technical breakdowns of the research changing deployment economics. If you have implemented a label-free optimizer in production, leave a comment about what failures you encountered first. You can find deeper analyses of these proxy problems in the Human Architect's full research tracking. The drop in performance at iteration 10 is a modern version of a statistical warning we have known for 50 years. Always validate your results against the actual task you care about, and not just the metric your optimizer is able to see.